We're just going to work a few more logistic growth examples, and that'll give us a better idea of how to manipulate this function into the form that we need for logistic growth. dp dt equals little k times p times the limiting factor 1 minus p over big K. So a population of polar bears is represented by the logistic differential equation where t is measured in years. So we have dp dt equals 0.08p minus 0.00004 p squared. Find little k and big K, the carrying capacity. So you have to do this oftentimes on the AP, so we need to be able to manipulate from this form into this form, and that's just algebra, but believe it or not, it can get a little intensive sometimes. I like to, you may have a completely different way for you to do it, and if you do, knock yourself out. I like to go ahead and turn things into fractions. We have 1, 2, 3, 4, 5 zeros here, so 100,000 p squared. I am going to simplify things. There's a 4 up top and a 4 down there that will cancel. And there's a 4 up top and a 4 down there that will cancel. Again, all of this is just algebra. I recognize now that I need to factor out from both of these terms 2/25 p. That's going to leave me a 1, and then it's hopefully going to leave me p over something, and that something's going to be big K. But right now I can tell that little k is going to be 2/25. So let's see here. Algebraically, 2/25 times 1 over something is going to have to equal 1 over 25,000. So I recognize there's going to be 1,000 down here, but I've got to take care of this 2 as well. So that's actually going to be 2,000. So our carrying capacity, big K, is 2,000. And that just takes some practice. You may have a completely different way that you want to do it. I like to do it where there's not a calculator present because many times we're going to encounter logistic growth where a calculator isn't present. So you need to make sure you can do that without the calculator there to help you. All right, the growth rate of a population P of bears in a newly established wildlife preserve is modeled by the differential equation dp dt equals 0.008p times the quantity 100 minus p, where t is measured in years. What is the carrying capacity for bears in this wildlife preserve? Well, again, not shockingly, we're going to find ourselves doing this a lot. We're going to have to get this into the form where we have a factor that's 1 minus p over big K. We're asked to find the carrying capacity a lot. So we're going to have to factor a 100 out here. So we're going to have 100 times this, and then if we distributed 100 back through 1 minus p over something, how would we get 1 for an answer, right? Because that's basically what's here is 1 as far as a coefficient to p. So we would, and that 1 doesn't need to be in there, sorry, 100 times p over what equals 1. And so that would be 100, okay? 100 times 1 over what equals 1. So that's 100, because technically that equals p. I'm getting tired, y'all. All right, so there's our carrying capacity, okay? Big K is 100. What is the bear population when the population is growing the fastest? Remember, it is always half the carrying capacity. What is the rate of change of the population when it is growing fastest? So what is dp dt, and I'll go back up here to this form of it, when p equals 50. And so that's all we're going to do is just plug in p equal 50, and we're not going to, even take time to clean it up, but there's the answer to that. So these are not terribly difficult questions, and they sound a whole lot alike. You're going to get asked the same things over and over and over again. So for each equation, find the carrying capacity of the population, so find big K. Find the size of the population when it's growing fastest, that's always going to be half of big K. And find the limit as t approaches infinity of the population. Well, shockingly, that's going to be big K. See how much carrying capacity comes into it? So again, all we're going to have to do is just put these into the form of our logistic growth model. So this is something, obviously, in this context, you have to be able to pull up immediately. So dp dt equals, and I'm going to factor a 200 out front, 0.006p, and that's going to leave me 1 minus p over what? And we saw in that last example that that's going to be over 200. And we can check that. If we distributed that 200 back through here, we would have 200 minus p. So our carrying capacity is 200. It's growing fastest at half the carrying capacity, that's 100. And the limit as t approaches infinity for this population is the carrying capacity. So again, sometimes if it's in this form, you can recognize that actually there's your carrying capacity, and you don't have to do all of that work. So here we'll just cut right to the chase and say the carrying capacity is 700. It's growing fastest at half the carrying capacity, that's a population of 350, and the limit as t approaches infinity of our population is the carrying capacity 700.